Hi guys, you're welcome to my channel. Today we are going to be looking at Coulomb's law, and I would like you to pay max attention to this class. The whole of the things we are going to consider throughout this class is just about Coulomb's law, and then we are going to finish the class with top 4 questions on Coulomb's law. If you are yet to do that, don't forget to subscribe to this channel, like the video, drop a positive comment, and if you have a question, feel free to suggest your problem. Thank you as you do. When you talk about Coulomb's law, before we state the law, we have to understand what the law is actually binding. You know, the law is binding the relationship between charges. Now, where do we get charge from? Let's start from the word atom. When you talk about atom is made up of nucleus, and the nucleus is made up of proton and neutron, while electron is revolving around it. So we have proton, neutron, and around this is what? Electron. So in an atom, we have proton, we also have neutron in it. Then we have electron. But if you remember, we said an atom is electrically neutral. So if an atom is electrically neutral, does that mean that all these particles has no charge? No. They have charge, but because the number of positive is equivalent to the number of what? Negative. That what make it electrically neutral. Now, which is positive, which is what? Negative. This is what we know before. The proton is a positive charge and the electron is negative charge, while the neutron is electrically neutral. So in an atom, the number of proton is the same as the number of electron. Do we get that now? So that is why we have an atom to be electrically neutral. Now, when you talk about the charge of proton, one proton, we already know that it's positively charged. One proton is equivalent to 1.6 multiplied by 10 raised to power minus 19 Coulomb. So one positive proton, are you getting this now? That is when you talk about proton, we know that it's positively charged. So saying proton positively is like tautology. Cool. Okay guys, so one proton is equivalent to 1.6 times 10 raised to power minus 19 Coulomb. And since we don't have a fractional proton, that is, we don't have a proton like 1 over 2 proton or 3 over 2 proton, we don't have what? Fractional proton. Is either you have 1 or you have 2 or you have 3 or you have 4. Are you getting it now? That shows that proton is actually quantized. Are we together now? So if proton is quantized, electron is also what? Quantized. And that's what means, that simply means that they exist in a discrete energy level. Are we together now? Therefore, any charge that you want to have is going to be multiple of 1.6 times 10 raised to power minus 19 Coulomb, since there is no fractional proton. Are we together now? So electron, one electron is equivalent to negative 1.6 multiplied by 10 raised to power minus 19 Coulomb. You will see that they are of the same magnitude. Why this one is negative is because electron is negatively charged. Are we together now? Then proton is positively charged, but they are both quantized. That's why we said charges are quantized, because neither proton nor electron exist in fractional value. Do we understand that now? Cool. Now, let's quickly look at something. If I have a positive charge, let me call this Q1, and I have a negative charge, I'll call this Q2. Now, what will happen if I place these two charges against each other? We all know that whenever we have what? Opposite charges does what? Attract each other. That is, the positive charge is going to experience a force in this direction. Likewise, the negative charge is going to experience a force in the opposite direction. This force is equivalent to this force in terms of magnitude, but it is opposite in direction. Now, how can we get the value of this force? If the distance between Q1 and Q2 is given to be r, then we can find the magnitude of this force using Coulomb's law. Cool. What does Coulomb's law state? Coulomb's law states that the force of attraction or repulsion. Why do I say force of attraction or repulsion? Let's pause before we state the Coulomb's law. Let's quickly consider if I have a body of negative charge and this one is also negative charge. Because they are of different charges, what will happen is that this one would experience a force of repulsion from this, while this one will also experience a force of repulsion from this. Are we together now? Cool. So, because they repel each other, the force between them is a force of repulsion, even if it is equal in magnitude. Because these two attract each other, the force between them is going to be force of attraction. Why? Because they are of different charges. Are we together now? Now, if you are to determine the value for the magnitude of force, either for this one or for this one, that is what we use Coulomb's law for. Mind you, Coulomb's law is only applicable to a static body. When the charges are static, that is when we can use it. Not when the charges are in motion. Do we understand that now? So, Coulomb's law is peculiar to a static body only. Do you understand that now? Cool. What does the law state? Coulomb's law states that the force of attraction or repulsion between two charges is directly proportional to the product of their magnitude. That is, by the time I take the product of the magnitude of Q1 and that of Q2, this force, either that of attraction or that of repulsion, is proportional to their products. Are we together now? That is the first part of the law. Then the law continues and say that same force that is proportional to the product of their magnitude is also inversely proportional to the square of their distance apart. That is the distance between Q1 and Q2, which is r. This force of attraction or this force of repulsion is inversely proportional to the square of it. Are we together now? And this gives us the second statement of that particular law. Now, we can now look at this now as a joint variation. So we then have that F is proportional to Q1, Q2 divided by R squared. And this will be our third statement. If I'm to remove this proportionality sign, I'll need to introduce a constant. So I think I'm running out of space. Therefore, I have that F equal K Q1 Q2 divided by R squared. Now, if Q1 equal Q2, then we have that F equal K Q squared divided by R squared. Are we together now? Where R is the distance between the two charges and F is the force of attraction or repulsion. If the two charges Q1 and Q2 have the same charge, either positive positive or negative negative, this force is going to be force of repulsion. But if their charges are opposite, that is, if one is positive and the other is negative, this force will become force of attraction. Do we understand that now? Good. And this is what the distance between the two charges. Now, what is the value for K? K equal 1 over 4 pi epsilon naught. So 1 over 4 pi epsilon naught is equal to 9 times 10 to the power of 9 Newton per Coulomb square per meter square. Are we together now? Cool. That is the value for our K. And we have to note this value because we are going to be using it while dealing with problem on Coulomb's law. Cool. There's something else that we need to understand here. What is the value for the epsilon naught? Epsilon naught is known as the permittivity of vacuum. And the value for the permittivity of vacuum is 8.85 multiplied by 10 to the power of minus 12 Coulomb square meter square per Newton. Do we understand this now? Cool. If that should be the case, then we can do something else. Okay, I think there's mistake here. So this is supposed to be Coulomb square per Newton meter square. Cool. Okay, so if that should be the case, we can then what? We can then do something else here now. What is the something else that we need to do here, or that we need to understand here? You can only use K to be 9 times 10 raised to power 9 Newton per Coulomb square per meter square if and only these two charges are in vacuum or in air. Are we together now? But if they are in water or any other medium, how do you calculate using the Coulomb's law? What you need to do is that you will be given the relative permittivity of that medium. So for you to get the permittivity of a medium, permittivity of any medium is equal to relative permittivity multiplied by the permittivity of vacuum. Are we together? Permittivity of any medium is equivalent to relative permittivity multiplied by the permittivity of vacuum. Therefore, the value for K will then change to become K equal 1 over 4 pi. Instead of epsilon naught, you are going to have epsilon r multiplied by epsilon naught. And this is what you are going to use to replace K. Are we together? Remember, I can rewrite this equation to become Q1, Q2 divided by 4 pi epsilon naught r squared. This is when the two charges are in vacuum. When you have the two charges in vacuum, we use this particular equation. But if you have it in other medium, other than vacuum, you have the equation to become F equal Q1, Q2 divided by 4 pi epsilon r multiplied by epsilon naught, where epsilon r is our relative permittivity and this is permittivity of vacuum, then multiplied by r squared. So this is what we are going to use in case. But often we always have the charge to be in vacuum, or we consider it to be in air. Are we together now? So, but in case question warrant this, you know how to go about it. Do we understand this now? Cool. Before we now start looking at questions under Coulomb's law, I want us to understand how all these factors affect the magnitude of the force. Now, we can see that F is proportional to Q1 and Q2. Therefore, if the magnitude of the charges is very, very high, are we together now? Once their magnitude is high, then your force of attraction or repulsion would also be what? High. Like if I have a charge of 2 microcoulomb and I have a charge of 50 microcoulomb. Now this is quite greater than this. Are we together now? So the force of attraction or repulsion that this one is going to create will be more than that of this. Are we together now? Cool. Now what happens again if you increase the distance? Once you increase the distance, because this force is inversely proportional to the square of the distance, increasing the distance will cause this force to reduce. Are we together now? But if you reduce the distance, it will cause this force to be greater. Do we get that now? Cool. So we can go to the next aspect of the class now. Okay. Now, before we start looking at the question, I would like us to look at some certain conversion that will be very, very useful for us. Like if I have 1 coulomb, okay, let me take it like this. If I have 1 millicoulomb, this is equivalent to 1 times 10 to power of minus 3 coulomb. And if I have 1 microcoulomb is 1 times 10 raised to power minus 6 coulomb. And when I have 1 nanocoulomb, this is 1 times 10 raised to power minus 9 coulomb. 1 picocoulomb is 1 multiplied by 10 to power of minus 12 coulomb. We have to understand all these conversion units. Why? Because the charges we might be dealing with are very, very small. So there is always need for us to convert them to coulomb. And if you have to do your conversion, you must memorize all of this. Are we together now? So, one proton is 1.6 times 10 to the power of minus 19 coulomb. This is very, very small. So even if I have 20 proton of charge, are we together now? This will still be very, very small. This is negative 19. It's very thousand, and that's why we always express them in microcoulomb or nanocoulomb or millicoulomb or picocoulomb. And at every instance, you always need to convert them to their appropriate unit, which is coulomb, and that's the essence of this. The same thing goes to the distance between them. If I have 100 centimeter, this is equivalent to 1 meter. Are we together? And when I have 1000 millimeter, this is what will give us 1 meter. You should memorize these two very, very well. They are also useful. Cool. I think now we are good to go for the questions now. Okay, so now let's look at question number 1. So question number 1 states that, I would like you to pay max attention now. A force of 400 Newton. The force is 400 Newton. Exists between two identical point charges separated by a distance of 30 centimeters. Calculate the magnitude of the 2 point charges. Are we together? So that's the question. So now let's interpret the question now. Having to understand what the examiner is requesting from us. Cool. A force of 400 Newton, we have our F to be 400 Newton, exists between two identical point charges. That is, this force is between charge Q1 and Q2, but Q1 is equal to Q2. Let me say equal to Q. Okay? Cool. And the distance between them is 30 centimeters, and we are looking for the value of the two identical charges. How do we go about that? Before we go on, the first thing I would like us to do is to convert this R to meter because it's in centimeter. And to do that, we just divide by 100. That is 30 centimeters. Since we know that 100 centimeters is what make a meter, then we multiply by 1 meter divided by 100 centimeters. Therefore, this and this would cancel, and this will cancel this. Then our R will become 0.3 meter. So we recall that the relationship between F, R, and Q is given by Coulomb's law. F equal K Q1 Q2 divided by R squared. And remember, I told you, or we know, that when Q1 is equal Q2, then we can just write this equation as K Q squared divided by R squared. Do we understand this now? Cool. The value for K, remember, we have it to be a constant, and that is 9 times 10 raised to power 9 Newton per Coulomb square per meter square. Cool. So F, we are given the value for F to be what? 400 Newton. So we have 400 Newton to equal, the value for K is 9 multiplied by 10 to the power of 9 multiplied by Q squared. We don't know the value. Then the value for R is 0.3 R squared. So if I cross multiply, I have 400 multiplied by 0.3 square will give us what? Okay, that will give us 0.09. And this equal 9 times 10 to the power of 9 Q square. So the value for Q square is just equal 400 times 0.09 divided by 9 multiplied by 10 to the power of 9. Cool. So we have, so this will give us 36 divided by 9 multiplied by 10 to the power of minus 9. So 36 divided by 9 should give us 4. So Q square equal 4 multiplied by 10 to the power of minus 9. Is that what we are looking for? No, because the question never says the product of the two identical charge. It says the value for the two identical charge. Okay, so what we need to do is to take the square root of both sides. So when we take the square root of 4 multiplied by 10 to the power of minus 9, this is the same thing as saying Q equal the square root of 4 multiplied by the square root of 10 to the power of minus 9. Are we together? Okay, if that should be the case, Q will be 2 multiplied by, then the square root of 9 is going to give us what? Okay, can that be? Okay, no. If I write this one, this will become 10 to the power of 9 divided by 2, and that will give us 10 raised to the power of minus 4.5 Coulomb. Are we together? So this will give us the value for this particular identical charge. Are we together there? Good. So let's take a look at something. Okay. Okay, so I can express this as Q equal 2 multiplied by, okay. So this can give us 6.32 multiplied by 10 to the power of minus 5 Coulomb. Do we get this now? So if I want to write this as microcoulomb, I'll say Q equals 0.63 microcoulomb. So the value for the 2-point charges is 0.63 microcoulomb each. Do we understand that? Because by the time you move this one forward, then we have okay, what am I doing? I think I'm doing the wrong thing here. Sorry. This is supposed to become 63.2 times 10 to the power of minus 6. So Coulomb. And this is equivalent to 63.2 microcoulomb. So that will be the value for the identical charge. So that's for question 1. So let's go for question 2 now. So as for the second question, we have that a positive 5 microcoulomb point charges is 20 centimeter away from a negative 15 microcoulomb point charge. What is the magnitude of the electrostatic force between them? Okay, and I think we can read the question now. So we have the first charge Q1 to be positive 5 microcoulomb, and the distance is given as 20 centimeter. And we have the second point charge to be negative 15 microcoulomb. So we are looking for the value of the electrostatic force between them. So where K is 9 times 10 to the power of 9 Newton per Coulomb square per meter square. Okay guys, here we have. What we need to do here is this. We'll first of all convert this to meter. So we have this to be 0.2 meter. Good. Is this force going to be attraction or repulsion? Definitely. It's going to be force of attraction. Cool. So we have from Coulomb's law, F equal KQ1, Q2 divided by R squared. Therefore, we have 9 multiplied by 10 to the power of 9. Then multiply by, remember we have to convert this one to Coulomb. So if this one is 5 microcoulomb, we have to multiply it by 10 to the power of minus 6. We said that earlier. So this will become 5 multiplied by 10 to the power of minus 6. Then multiply by 15 times 10 raised to the power minus 6 divided by 0.2 all squared. So the electrostatic force of attraction becomes 9 multiplied by 5 multiplied by 15, then multiplied by 10 to the power of 9 minus 6 divided by 0.2. This is supposed to give us 0.04. Cool. And I can write this one as 4 multiplied by 10 to the power of minus 2. I think this is awesome. Cool. Okay, so we have 9 multiplied by 5 multiplied by 15. That will give us that F equal 675 multiplied by, this will give us minus 12. Then minus 12 plus 9, that will give us minus 3. So this is 10 to the power of minus 3 divided by 4 times 10 to the power of minus 2. So 675 divided by 4, what do we have? So we have the F to equal 168.75 multiplied by 10 to the power of minus 1. So if that should be the case now, if this is 10 raised to the power minus 1, because this one will become plus, then we have just what? Minus 1, which is equivalent to, like, we are dividing by 10. So this will give us F equals 16.875 Newton. So F is equal to 16.9 Newton. So this is going to be the value for the electrostatic force of attraction between the two charges. So for the third question now. Okay. So for the third question, we have that determine the net electrostatic force on point charge B as a result of the other two charges. Assume that all charges are stationary. So we need to look at the diagram here. So here we have a point charge A, and this is a positive charge. And we have a point charge B. This is negative 12 microcoulomb. And we have another point charge C, and this is just positive 2 microcoulomb. The distance between B and C is given as 4.0 meter, and the distance between A and B is given as 3.0 meter. So the question says we should look for the value of the electrostatic force on point charge B if all these charges are stationary. Now, the reason why they told us that the charges are stationary is for us to understand that we can apply what? Coulomb's law. Cool. Now, how do we go about that? Well, first of all, look for the force between these two. That is the force of attraction between A and B. So we have that FBA equal KQB and QA divided by R squared. So this will in turn give us 9 times 10 to the power of 9 multiplied by 12 microcoulomb is the same thing as saying 12 times 10 raised to the power minus 6 coulomb. Then multiplied by 10 microcoulomb is 10 times 10 to the power of minus 6 divided by the distance between them, and that is 3 squared. So we have that FBA equal 9 times 12 times 10. Okay, I don't need to do this. So this is going to become 10 to the power of minus 5. So I can just go by saying 9 multiplied by 12, then multiply by 10 to the power of 9 minus 6, then minus 5. Do we understand this? Divided by 9. So this and this can cancel. Then I have that the force of attraction between A and B is equivalent to 10 to the power of, this will give us 11. 9 minus 11 will give us minus 2. So this is what we have. Cool. Now that we're done with this, we can then calculate the effect of this particular force on C on B also. So we are going to look for FBC. FBC is also going to be KQB multiplied by QC divided by R squared, where R is the distance between them. Cool. So that will be 9 multiplied by 10 to the power of 9, then multiplied by 12 times 10 to the power of minus 6, multiplied by 2 times 10 to the power of minus 6, divided by our R, that is 4 squared. Cool. Therefore, we have that FBC is equal to 9 times 12 times 4 times 2 rather. So 9 times 12 times 2, then multiply by 10 to the power of 9 minus 6 divided by 16. Cool. So F of that will give us 9 times 12 times 2. So that will give us 216 multiplied by 10 to the power of minus 3 divided by 16. Can 16 divide 216? Good. We have 13.5. So we have that FBC is 13.5 times 10 to the power of minus 3 Newton. In other words, BC equal 1.35 times 10 to the power of minus 2 Newton. Okay? So we've gotten the value for this and this, but we are asked to look for the net force charge on this. Abi? So for us to know the value for that, we have that the net force is going to be the square root of FBC square plus FBA square. Are we together? So the net force is therefore equal the square root of, this will give us 0.01, if I'm not mistaken, yeah, 0.01 all square plus this one will give us 0.01, yeah, 0.01 also, if I'm not mistaken. Okay, let me check. Divide 1.35 divided by 100. So that will give us 0.0135. So okay, let me just put this as 4 all square. So that it will be a significant difference there. Okay, we therefore have that the net force is going to be the square root of 0.01 square. Okay, that will give us 1 times 10 to the power of minus 4 plus the other one 0.014 all square. So this will give us 1.96 times 10 to the power of minus 4. Okay, so permit me to create space here. So the net force is just going to be the square root of 1.96 plus, so that will be 1 plus 1.96 multiplied by 10 to the power of minus 4. Do we get this now? Okay, if that should be the case, we can then say the net force is going to be the square root of 2.96 times 10 to the power of minus 4. Do we understand this now? So let's quickly check. Okay, 2.96 multiplied by 10 to the power of minus 4. So what will be the square root of the answer? So this will just give us that the net force is 0.017 Newton. So that's our result. Okay, let's go for the last question now. Okay, for the last question, we have that 3-point charges are located at the corner of an equilateral triangle with a side length of 2.0 meter. So let's draw the equilateral triangle. So let's say this is Q1, Q2, okay? Okay, let me say this is Q3 and this is Q2. This is 2 meter, 2 meter, and 2 meter. Cool. Okay, then we are told that Q1 is equivalent to 6 microcoulomb, but it is positive charge, and Q2 is negative 12.0 microcoulomb, and this one is also negative 5 microcoulomb. Calculate the net electrostatic force on point charge Q3. Assume charges are stationary. Okay, and this will be our last question for today. How can we look at the value for the net charge on this? Okay, for us to solve this question correctly, what I would like doing is for us to draw a free body diagram of how the force actually affected. Remember that Q2 and Q3 is going to produce an horizontal effect. So that is, the force of repulsion is going to take place along the horizontal axis towards the positive what? Positive charge. Are we together now? Because it's going to repel this towards this side. Cool. And if you look at the effect of Q3 of Q1 on Q3, it's going to be force of attraction. That is going to cause Q3 to move in this direction. Are we together now? So if it causes Q3 to move in this direction, then we can then find the value for F1, F32 and F31. Are we together now? Okay, so how can we find that? For us to get the value of this, because these two forces are not perpendicular, are we together now? And they are not parallel. So we have to use the resolution of vector in solving this. So we have to resolute the value for the horizontal forces and the value for the vertical forces. Now for this one now, F what? For the horizontal component of this, remember that this angle between them is going to be 60 degrees since it is an equilateral triangle. Cool. So this is going to become what? F32. Are we together now? Then plus the horizontal component of this particular force. This is F32 now, which is the horizontal component of this. Are we together now? That is the force of attraction between these two. Then for this one now, because this body now is moving, the x component of this one is towards the negative axis. So instead of having plus, we are going to have a negative. Then this angle is also 60 degree. Sorry. So we are going to have F31 to be cos of 60 degree. Are we together now? So, and for the vertical component, this one does not have a vertical component. Thus, the only vertical forces that we have is that of this. So it's going to be F31 sine of 60 degree. Are we together now? Cool. So we can just see the summation of the horizontal forces. F32 is going to become 9 times 10 to the power of 9 multiplied by 12 times 10 to the power of minus 6, then multiplied by 5 times 10 to the power of minus 6, divided by this distance between them is 2 squared, plus F31. F31 is going to give us what? Okay, F31 is going to give us 9 times 10 to the power of 9 multiplied by 5 times 10 to the power of minus 6, then multiplied by 6 times 10 to the power of minus 6, divided by 2 squared, then cos of 60. So cos of 60 degrees to multiply this. So all these are like this. Cool. So I have that the summation of the horizontal axis is going to be 9 times 12 times 5, that should give us 216 if I'm not mistaken. 9 times 12 times 5, okay, that's 540, okay? So we have 540 multiplied by 10 to the power of minus 3 divided by 4 plus, it's not going to be plus, sorry, it's supposed to be minus. So minus, this will give us 9 times 5 times 6. 9 times 5 times 6, that gives us 270. So this is 270 times 10 to the power of minus 3 divided by 4. Okay, so the summation of the forces along the horizontal axis becomes 540 divided by 4. That gives us 135 times 10 to the power of minus 3 minus 270 divided by 4, that will give us 67.5 times 10 to the power of minus 3. So we have that the summation of the horizontal component forces is going to be 135 minus 67.5 times 10 to the power of minus 3. And that will give us 67.5 times 10 to the power of minus 3 Newton. So that's the value for the summation of the horizontal component. Then for the vertical component, the summation for the vertical component is therefore F31. You know, F31 results to 7.5 times 10 to power of minus 3. Okay, I think there's a mistake somewhere here. Sorry. We don't multiply this by cos of 60. I know cos of 60. Sorry, that's a very nice observation now. Okay, cos of 60 is 0.5. So we need to multiply that. 7.5 multiplied by 0.5. That will give us 33.75. So the summation of the horizontal component is 135 times 10 raised to power minus 3. Okay, sorry. Minus 33.75 multiplied by 10 to power of minus 3. So what will this give us? This will result to 135 minus that. This will be 101.25 times 10 to power of minus 3 Newton. So back to this now. You know, this particular one will result to this, right? So if that should be the case now, sine of 60 degrees. So the summation of the vertical component therefore becomes 7.5 sine 60 degrees. So that will give us 58.5 times 10 to power of minus 3 Newton. But is that our answer? No, that's not the final answer. So we can find our final answer by doing this now. So we therefore say that the net force on Q3 is the square root of our result here. Wow. Okay, I think there's a problem now. We forgot to write this down. So now we be, okay, we can get that easily. 135 minus 33.75. Okay, so that will be 101.3 all square plus 58.5 all square. Then everything multiplied by 10 to power of minus 3. Okay? Okay, I think for us not to make a mistake here, so I think this result is not correct. 101.3 times 10 to power of minus 3 all square plus 58.5 times 10 to power of minus 3 all square. So to avoid mistake, so the net electrostatic force on Q3 will become, okay, this will give us the square root of 25 times 10 to power, 1.6 times 10 to power of minus 3 plus 58.5, supposed to become 6. Okay, so this will give us 3422.25. 0.3 times 10 to power of minus 6. Cool. Okay, so the next force becomes the square root of, so I can have these two together, 10 25 1.6 plus the results will give us 13673.85 times 10 to power of minus 6. Okay. Okay. So the square root of our results. So the net electrostatic force is equal to 0.12 Newton. So that's our result. It's as simple as that. So at this junction, we call it a day. Don't forget to share this video with your friends and wait for more reasonable lecture on physics. Thank you.